Hello, this is my Lab 4 presentation. So what is this lab about? Well, it's about circuits, how they work, and how different components of a circuit work, such as resistors and capacitors. The primary law that we used in this is Ohm's law, which is V equals IR, or any combination of that. This is a useful little triangle for that. Okay. So initially, I'm going to look at some observations. They asked us to observe the potential differences at these different points, A, B, C, D, E, F, G, H. And this is what I found. At the batteries, it was 1.5. CD was negative 0.959, negative 2.041. This essentially means it's going down. It's going down. This is going up. This is going up. And the important thing is that it all sums to 0. And another observation to note is that it was 0 at FG and HG, which is where the wire is and where the ammeter is. And this flows into the next part, which is looking at the resistance of this circuit at different points. Because the voltage was 0, the potential difference was 0, the resistance of the wire and the ammeter is going to be 0 since R is equal to V over I. And because of that, that means that the resistors are going to be what we determine they are, which is 47 ohms and 100 ohms. Next, the time we looked at the time it takes to discharge a 20 millifarad capacitor from with a 10 ohm resistor within the circuit, and it looks something like this. And that took 9.42 seconds, and for a 20 ohm resistor, it took 18.3. And this makes sense because with a higher resistance, since I is equal to V over R, a higher resistance means a lower current, and because this is a lower current, it's going to take longer to discharge. Additionally, a big part of this was calculating the RC value. So using the slope that we found over 20-second interval, going by 1 second intervals, I found that the RC value was 6.006. And the actual RZ value, which is calculated by resistance times the capacitance, should be 6. So I got very, very close with this slope approximation here using Excel. As a conclusion, here's some questions. What if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's the difference? So a real ammeter would likely have some resistance, so that would mess with your current readings, and that's essentially exactly what it would do. So the second question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would your ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So in real life, the real battery and the real capacitor, in that instance, the battery would just explode. It'd go boom. And in this simulation, it just charges the capacitor instantaneously. That's it for my presentation. Thank you very much.